Hi guys, welcome to lesson 21-2. We will be starting here on page 363 in your book, and we've got a couple goals today. We're studying population growth, so how that's different from your compound interest functions, just little intricacies that are a little bit different. So we're going to create functions to fit population data, interpret values in those functions, and compare exponential and linear population growth. As always, comparing exponential and linear and seeing some similarities and differences. So let's get cracking. You probably already figured this out, but I didn't mention this lesson starts on page 347 in your book. So the population of Nevada since 1950 is shown in the table in my notes section over here. We're going to graph the data from the table. And so 1950, 160 down here, 285. Let's see, that must be 2. Okay, so 1980, 800, 1.2 million. All right, about like that. And when we use the table and the graph to explain why the data are not linear, the table does not show a constant rate of change. I knew you already knew that. And the graph does not show a line, obviously. That's why it's not linear. It doesn't show a line. It shows a curve. All right, so on this one, you should pause it to finish filling this in, because I'll just fill it in real quick. But we're going to complete the table by finding the approximate ratio between the populations in each decade. So the ratio of this to this would always be the newer one over the older one. So the current population divided by the previous decade's population. So the next one will be 488 divided by the one before it. So this one will be 800,508 divided by 800,508 divided by 488,738. And that's going to give you, and it looks like they're going to the, oh, we didn't finish this one. This one's going to give us 1.713. They're going to the thousandths. These are approximate. That's why the equals is a little wiggly. 1.638 for this one. And then this one will be 1,201,833 divided by that 800,508, which gives us approximately 1.501. And then this last ratio, 1,998,257 divided by 1,201,833 will be about 1.663. So make sure you're able to do this stuff precisely and your rounding rules are not being ignored and all that. So we want to explain how the table shows that the data are not exponential. So we knew before that the data wasn't linear because there wasn't a constant rate of change and it wasn't a line on the graph. But we can also tell it's not exponential because the ratio isn't the same. There's no common ratio, which means there is no constant factor. So there is not the same ratio or a constant factor being multiplied each time. The data are not exactly exponential, but the shape of the graph resembles an exponential curve. Also, the table in item 3A shows a near constant factor. So 1.78, 1.71, 1.6, 1.5, 1.6 are almost the same. So these suggest that the data are approximately exponential. So what we'll learn to do is use exponential regression to find an exponential function that models the data. We're not going to find a function that's a perfect fit because the data isn't exactly exponential, but we can use a regression to find something that's close. So number 4 says, use a graphing calculator to determine the exponential regression equation to model the relationship between the decades since 1950 and the population. So the way we're going to do that, if we're using GeoGebra, is we're going to do view and spreadsheet, and we're going to enter a couple columns of data. So these will be the decades since 1950, so we'll have 0, 1, 2, 3, 4, 5 straight from the table. And then these will be the population. So we don't want to put commas, so 160,083 is the first one. 285, 278 was the second one. 488, 738, 800, 508, 1,201,833, and 1,900,098 to 57. All right. So then what we'll do is we can highlight all that, and then we're going to come over here under analysis, and we're going to drop it down, and we're going to pick 2-variable regression analysis. And then we'll tell it to go ahead and analyze. And then under regression model, we want to pick growth. And that's going to show us the equation right here. And the book says that the calculator gives us A and B, and that's what these are right here. So this is A, so approximately 170,377, and B is approximately 1.645. So we can fill that in on the book. So from our graphing calculator, we came up with A of 170,377 and B being 1.645. And GeoGebra actually already showed us the general form of that equation, y equals A times B to the x. So it looked like y equals 170,377 times 1.645 to the x power. And then we're going to sketch what the graphing calculator gave us. And so remember that 4 times 10 to the 5th, here they go again with these scientific notations, but that means 400,000, 800,000, 400, 800, 1.2 million, and so on. So when you sketch from a graphing calculator, you're going to use a similar scale and find approximately. So this was about the points that we had before. And the regression line looks like kind of like that. And so there's some little points off a little bit. It doesn't fit just perfectly, but you can see the line is kind of like a line of best fit. So is this exponential function a good approximation of the data? Explain, yes. The data fits the graph very closely. So the line closely. The line fits the data points, the curve fits the data points very closely. Maybe not perfectly because there's not a constant factor, but very, very close. All right, so first we're going to tell here what does the value of B tell us about the population growth. So since B is bigger than 1, we know it's growth. And what exactly is that growth? So you want to look at what is it above 1 that's getting multiplied every time. So the growth rate is about 64.5%, because that would be 0.645, which is what's getting added here to 1. The value of A is the population 0 decades before 1950. So that's the population at 1950, and it's also on the graph. How is it related to the graph? That would be the y-intercept, because x is the decade since 1950, so it would be at 0 decades. Now, if we want to estimate the population in 1995, let's see. So remember, this first decade would be just to help us think this out. One decade would have been 1960, and that would have been 1970, 1980, 1990, and then this would be 2000. So if we want to estimate what will the population be in 1995, using the function, we'd have to plug in how many decades since 1950 would this be? It's 45 years, right? Since 1950. So how many decades is that? That would be 4.5 decades. So we could plug 4.5 into the function, and that would tell us the population at 1995, or 4.5 decades since 1950, because that's what our function was based on. On the graph, we would look at the function between x equals right there and right there. So x equals 4 and x equals 5, and we'd see about what that was. So it looks like it's going to be, right about 160,000 or so. And at a table, we'd kind of do the same thing. We would look between the x equals 4 and the x equals 5 numbers on the table and see what were these outputs here, and look at that output and just determine what was between those. So now it wants us to actually estimate that population in 1995, and it wants to know which method we chose to use, a table, a graph, or a function. So I really want you to decide what way you want to use. So I always rely on the function. I just think it's easier than trying to guess from a table or from a graph exactly what that would be. So I'm going to plug it in and do 170, 377 times 1.645 to the power of 4.5. Do it yourself and see what you get. So depending on how you round it and when, you should come up with something like 1,600,138.33. Well, we'll call that 138, right? So about 1.6 million. And I just realized I accidentally said on number 7 when I was predicting about 160,000. So that's the other thing dangerous about using graphs is if you're using different scale or powers like this, you accidentally use the wrong unit. So not 160,000, but 1,600,000 would be a closer estimate. So now we want to estimate, and why I use the function, I just thought easier to be precise than looking in between values on a graph or a table. So if we want to estimate the population in 2010, that's going to be 60 years, right? 60 years. So our decade, 60 years after 1950. So our decade is going to be 6. Our power will be 6. So calculate that up and see what the population would be there. So again, depending on how you entered and what you rounded before you multiplied, you should get something about 3,376,031 for your population. Now, this is a really great question to think about. Which estimate do you think is likely to be more accurate? I want to talk about this in class, so remind me. Your estimate from 1995 or 2010? And explain. So pause this and take a couple minutes to think about which one you think would be more accurate and why. So 1995 is likely to be more accurate because it's closer to the data. It's closer to the existing data. And the farther out you go is assuming that the pattern continues, which we're not sure that it does. It could be that something happens that causes the population to start shrinking. Certain generations have more kids than others, and we don't know that it will continue. So the farther out we go, we don't know that that pattern will continue, so our estimates will probably become less and less accurate. So if we were looking at our GeoGebra regression, our exponential regression, a couple things we could do. We could use this tool right here to view the data, and that'll let us view the table. And we also have this tool down here that lets us evaluate the function, and we can put anything we want in. So if we put 4.5 in for x, and then hit enter, it'll tell us the value of the function there. And it looks like we'd have 1,601,907. So that's a little peek at GeoGebra. So sometimes we want to take a growth rate that we have and look at it in terms of a different time frame. So the function we have now estimates the growth per decade. We can use that rate, that 64.5%, to estimate the growth per year, or the annual growth rate. So what we need to do is let n be the number of years since 1950, and write an equation that gives the number of years in terms of decades. So there's 10 years per decade. X was our decades. So if we solve this for x and divide by 10, we'll get x equals n over 10. So when we took this, solve for x, and that is going to show us how to figure out the annual growth rate. Now we're going to rewrite the function that we had that models Nevada's population, and then we're going to write it again, but replace x with the equivalent expression that we just came up with. So here's the original one, 170, 377 times 1.645 to the x. And so the new one is going to be y equals 170, 377 times 1.645 to the n over 10. And now we're going to simplify to write the function in this normal form, okay, without a rational power, without a fraction power. So this is very simple, but see if you can follow it. Here's what we are starting with, right? Here's what we just wrote. And we want to break it down so that this power out here is not a fraction. So if you remember what happens when you multiply, remember if you had x squared to the power of 3, powers of powers multiply, right? So this would be x to the 6th. So if I have n here and I put the 1.645 to the 1/10 times n, that means that 1/10 and n, 1/10 times n, would give me n over 10. So basically, I just separated those, so I have to the nth power, right? So now we want just a value in here, okay? So something to the nth power. So we have to figure out what 1.645 to the power of 1/10 is. And so you can plug it in like, you know what 1/10 is. You can plug it in as a fraction if your calculator lets you, or you could do 1.645 1.645 to the power of 0.1, because 1/10, or 1 divided by 10, is 0.1. So do that. 1.645 to the power of 1/10 gives you 1.051. So there's our new function. So the yearly growth rate was 5.1%, right? And we can use that to find an annual. We could plug in single years now instead of just decades. So the approximate annual growth rate, just sort of mentioned that, is 5.1%, because the new growth factor was 1.051. So the 0.051, if I turn it back into a percent, move that decimal 2 places, I'd have 5.1%. That's how I know. So to find the approximate population of Nevada in 2013, what value should we use for n? Well, we're going to use, let's see, how many years is it from 1950 to 2013? If I do 2013 minus 1950, just to make sure we don't make mistakes, right? 63 years. So n equals 63 because it's 63 years since 1950, and we now have an equation that's an annual rate based on the number of years. So if we use this to predict the population in 2013, we would have 170,377 times our annual rate, 1.051, or approximately 5.1% a year, for 63 years. So go ahead and calculate that yourself. Let's see if we come up with about the same thing. So hopefully you came up with something approximately 3,911,849 people that year. So here we have a case where the population of the town of Shady Gap can be modeled by the function this, and the population of the town of Oak Grove can be modeled by this g function. So x is the number of years since 1990. So let's describe the population growth of each town. So Shady Gap, what does it look like it started? Looks like it started with about 10,240 people in 1990 and grew by 65 people each year, right? Because that's a linear function there. And it wanted us to talk about that. Identify the type of function. So this is shown by a linear function. It had a constant rate of change of 65, so it's just increasing 65 people every year. And then Oak Grove looks like it started in 1990 with, or had a population of 8,964 people, little town, in 1990, and grew by, that looks like 1.5% every year. And that is shown by an exponential growth function, because it's got a factor bigger than 1, which is making it growth, and that power of x, that's the exponential function, a times b to the x. So now it wants us to enter both functions in a graphing calculator and then use the table feature to try to figure out when both of the populations were the same, or the point of intersection, and then also use just the graphing function to find that point of intersection. So go try to do that on your own in GeoGebra, and we'll see how you do. So I've already input my two functions, my f of x and my g of x, and then I changed my x-axis to go from 0 to 20 and my y to go from 0 to about 20,000 or so. And then I used the point tool to select both lines and click a point and see that they cross at about 15 years, approximate population of 11,220. So generating a table of values in this program is sort of cumbersome, and you could do one by hand and just plug in x's to each of your functions and see what they are each year until they're about the same. But you understand that process, and it's sort of defeating the purpose of the tool to have to plug all those in by hand when we've already created the formula. So there's a way to take a peek at the graph. So we didn't really use the table function, but if we did create a table and we plugged in a bunch of x's and got a bunch of y's for each of our functions, we would see that on the 14th year, f of x was still higher, but then on the 15th year, f of x was still higher, and then on the 16th year, g of x was higher. So it crosses sometime about 15, and we would see that it was somewhere between, you know, a little above 11,000. So we'd probably come up with something like that if we use the tables. On the graphing calculator, we actually came up with, let's see, 15.02, and it was like 11. Oh, that's rough there, but approximately that. So if we interpret our answer there, that means that just at about the 15th year, Oak Grove, is that the name of it? Yeah, Oak Grove's population will be the same as Shady Gap, approximately 11,200, and then Oak Grove will be higher if the patterns continue. So we always want to say that if we're predicting the future. They'll be approximately same at this population, and as long as the patterns of the functions continue, then from then on, Oak Grove will be higher than Shady Gap. So that just gives a little context to what we found out there. So we'll pick it up from here in class, and just make sure you bring your questions, bring your thoughts, and somebody remind me, I'd love to hear about your thoughts on 9b, what you were thinking before I said anything. I just like to know how your brains are working. Sometimes they're different from mine, and sometimes they're better. So we'll meet you in class.